Howdy, and welcome to lecture number 8. Okay, well, the reason why I've moved lecture number 8 to video content is because there is a lot of information in this lecture, and it's a lot of important information as well. We kind of throw a lot of information out in one single lecture, and because this is a critical lecture in terms of the information that you learn. In other words, it's material that you're going to use consistently through the rest of the semester. I thought that having it in video format where you can come back and reference it sometime later would be helpful for you. So this lecture is meant for you to be able to watch again, and so we put it in video fashion so that you're able to do that. And of course, we're going to put a lot of the concepts that you need to know in this video lecture, but then do examples for you in class so that you get a chance to actually see how this material is applied and used in thermodynamics. So the quick outline is that we're basically going to go over the pressure temperature phase diagram, temperature specific volume phase diagram, and pressure specific volume phase diagrams. And that will allow us to introduce a concept called the state postulate, and which will then lead us into a discussion about tables of properties, how we use the tables, the introduction of a new property called quality, the use of linear interpolation, and then finally the use of the saturated liquid approximation. So we'll go through all of these elements in the video lecture. Okay, so first of all, we've already talked about the pressure temperature, temperature volume, and pressure volume diagrams. But just as a quick summary, of course, these are phase diagrams, and so we can identify the phases of a substance on a phase diagram. And one example phase diagram is the pressure temperature plot, where, of course, we have the three phases: solid phase, liquid phase, and vapor phase, which is, of course, our gaseous phase. And the line that separates the liquid and vapor phase is called the vaporization line. This is where phase change occurs from liquid to vapor, or from vapor to liquid. And the line that separates the solid-liquid phase is called the fusion line. And then finally, we have the line that separates the solid-vapor phases, which is the sublimation line. And so this is how sublimation process occurs. Where these three lines intersect is called the triple point. And the triple point, of course, is where all three phases exist simultaneously. And then the very tip of the vaporization curve is called the critical point. And we define the critical point as that where equilibrium phase change no longer takes place. Above this point, equilibrium phase change no longer takes place. And we'll talk about what that means more in just a little bit. And of course, we talked about how this phase diagram looks different for different types of substances. So for water, the fusion line is slanted backward, whereas for substances other than water, the fusion line is slanted forward. Okay, so we've also learned that pressure and temperature are what we call dependent during a phase change. That is, they're dependent properties during a phase change. What that means is that the temperature of a substance, or the temperature at which a substance changes phase, depends on its pressure, and vice versa. Okay. This also means, because the two are dependent, it also means that the temperature and pressure of a substance do not change as it undergoes phase change. But of course, other properties do change, right? So things like specific volume, internal energy, enthalpy, and entropy all change during phase change. And we capture the behavior of that phase change on a temperature volume, or temperature enthalpy, or temperature internal energy, or temperature entropy diagram, or PV, PU, pH, or PS diagrams. So I have written here that we can capture the behavior between these properties in either temperature or pressure on a T question mark or a P question mark diagram, where the question mark is either specific volume, internal energy, enthalpy, or entropy. So we're going to go through these two diagrams, the temperature question mark or the pressure question mark diagrams, and recognize that it really doesn't matter what this property on the x-axis is the shapes of all these curves are the same. Okay, and likewise, it doesn't really matter what the question mark is on the x-axis with the pressure diagram. The shapes of all the curves are the same, regardless of that x-axis property. Okay, so just for simplicity, what we'll do is we'll describe the temperature volume diagram. And so we have our temperature volume diagram, and remember that what we're doing here is we're basically taking the temperature pressure diagram, right? And we're recognizing that there's a third axis down here, and that third axis kind of comes out of the computer screen on us. And that third axis could be specific volume, for example. So if you can kind of imagine pulling that pressure temperature plane, pulling that in the third axis dimension, what happens with this vaporization curve is it becomes a dome. And that's what we show here on this temperature volume diagram. So this dome that you see is the vaporization line that has been extruded in the third dimension from a pressure temperature plot. Okay, so and this area under this saturation dome, this inverted parabola, is where we have a two-phase region. So what that means is that our substance exists simultaneously with two phases, a liquid phase and a vapor phase. So to the left of the dome, to the left of this line here, we have what is called our compressed liquid phase. So this is our, what we would typically call our liquid phase, but because we have a few different regions where we may have a liquid, we have to add some additional adjectives to clarify or specify exactly what type of liquid we're dealing with. So if the substance is to the left of this saturation dome, we call that a compressed liquid. Likewise, if the substance is to the right of the saturation dome, so out in this region here, we call that the superheated vapor region. So the substance would be a superheated vapor. And of course, if the substance properties are such that it's undergoing phase change and it's somewhere underneath the dome, then that means that it is undergoing phase change and there are two phases present in the substance simultaneously, liquid and vapor. And so we often call this the two-phase region, the two-phase mixture region, two-phase liquid plus vapor region, or just the saturation region. All those terms mean the same thing, and that is the substance is underneath the dome. Now you'll also notice that we have drawn on here two lines of constant pressure. So this is a line of constant pressure, and that line of constant pressure corresponds to what I've labeled as P1. And then we have a second line of constant pressure, and this line of constant pressure corresponds to what I've labeled as P2. Now, you have to remember the general shape of these pressure curves, and you have to remember that there's actually a typo here. I'm sorry. I need to fix that. This should be that P2 is greater than P1. So let me see if I can do this real time here. I don't know if I can do this. No. Okay. Let's see if I can just add text then. Not very easily. Okay. Well, anyway, just make a note that that's a typo here, and that this should be P2 is greater than P1. So I should say that P1 is less than P2. My apologies for that. Okay, so P2 is greater than P1. And of course, the tip of this dome is the critical point. So the critical point, just like it's the tip of the vaporization line, it's also the tip of the saturation dome. Okay. Okay, so now there are some additional features to this saturation dome that we need to be familiar with. Okay, so first of all, this line of the saturation dome that's to the left of the critical point, we call that the saturated liquid line. So remember how I said that there was a reason why we called this compressed liquid? Well, the reason is because if the substance is anywhere right on this line, somewhere along this line, then that is called a saturated liquid. Okay? So a substance that is a saturated liquid, what that means is that it's saturated, which is to say that it's about to change phase, but it's still completely a liquid. So in other words, it's at the saturation temperature and pressure, or if you prefer, the boiling temperature and pressure, but it's still all a liquid. It hasn't started to actually change phase yet. So a substance, when a substance is saturated, we say that its temperature is called the saturation temperature, and its pressure is called the saturation pressure. Okay? So if we say a substance is saturated, for example, it means it's at the saturation temperature and pressure and is about to change phase, whether it's about to become a liquid, if it's already a vapor, or it's about to become a vapor if it's already a liquid. So just like how the left-hand side of the dome is called the saturated liquid line, the right-hand side of the dome is called the saturated vapor line. So we have saturated liquid to the left of the critical point, saturated vapor line to the right of the critical point. Okay? So saturated vapor is the same concept as saturated liquid, except the substance is a vapor. Okay? So if the substance is on this line, it's said to be saturated, which of course means that it's about to change phase, but it's still completely a vapor. Okay? So we can be in several different locations. We can either be in the compressed liquid region, in which case we're a compressed liquid, we're not changing phase. We can be right on this line, which means that we're saturated liquid, which means that the substance is saturated, it's about to change phase, but it's still completely a liquid. We can be somewhere under the dome, which means that we're saturated. We're at the saturation temperature and pressure, so we're changing phase. And there's some kind of mixture of the substance where part of the mixture or part of the substance is vapor and the other part is liquid. We can be right on the right-hand side of the dome, right on the line, in which case we're called a saturated vapor. And so the substance is saturated, it's able to change phase, but it's all a vapor. None of the mixture, none of the substance has become a liquid. And of course, we can be out here in the superheated vapor region where we're all a vapor and we are not about to change phase. Okay? Okay, so as I just mentioned, a substance that is two-phase, that is, it has liquid and vapor phases present in a mixture of phases basically, that two-phase substance is saturated, and it's a mixture when a portion of the substance is saturated liquid and the balance is saturated vapor. So we're going to come back to this idea of a two-phase mixture a little bit later on. So let's suppose that a substance is at a given temperature and pressure and it's a saturated liquid, which means that it's on the right hand, it's right on the left-hand side of the line of the dome. So it's right on this line here. And in fact, what we're going to do is we're going to say that our substance is right here at this spot where that black dot is. So we're at a given pressure and we're at a given temperature and we're a saturated liquid. What we would then say is that the substance's specific volume is called the saturated liquid specific volume at the saturation temperature and pressure. And because that's a specific point in the temperature volume diagram, we subscript the specific volume with the letter F. The reason why we use the letter F is because the legacy tables, the legacy thermodynamics, thermodynamics from 100 years ago, didn't think in terms of liquid and vapor, they thought in terms of fluid and gas. And so if we are subscripting, or if we're intending the property to correspond to saturated liquid, we use the letter F. So when you see a property subscripted with the letter F, like we have here, we have V sub F, comma, T sat. What that means is this is the saturated liquid specific volume at this saturation temperature. Okay? And that's true for all our properties that we'll study. So V sub F T sat is the saturated liquid specific volume at saturated temperature. U sub F Tsat is the saturated liquid internal energy at saturation temperature. H sub F Tsat is the saturated liquid enthalpy at saturation temperature. And S sub F Tsat is the saturated liquid entropy at saturation temperature. Likewise, if a substance is at a given temperature and pressure and it's a saturated vapor, that is, it's right on the right-hand side of the dome, in other words, it's right on this side of the dome here, then we say that its specific volume is called the saturated vapor specific volume at the saturation temperature and pressure. So we subscript saturated liquid properties with letter F. Again, that is legacy meaning fluid. We subscript properties that correspond to the saturated vapor line with the letter G. And again, that's legacy meaning gas. So V sub G is the saturated vapor specific volume at the saturation temperature. In other words, if our substance is right here on the line where our little black dot is, then the specific volume of that substance is called the saturated liquid specific volume at that saturation temperature. And just like saturated liquid properties, it's also true that all the saturated vapor properties are subscripted this way. So V sub G Tsat is the saturated vapor specific volume at Tsat. U sub G Tsat is the saturated vapor internal energy at Tsat. H sub G Tsat is the saturated vapor enthalpy at Tsat. And S sub G Tsat is the saturated vapor entropy at the saturation temperature. Okay, so that's a lot of the information that we need to know about the temperature-specific volume diagrams. We also, I should say the temperature question mark, because remember, it doesn't really matter what's on the x-axis here, if we have V or U or H or S, okay? And the same is also true for the pressure question mark plots or phase diagrams. And the pressure question mark phase diagrams are very similar to the temperature question mark phase diagrams with one exception. And that one exception is the way that the lines of constant temperature appear. The lines of constant temperature on a pressure question mark plot appear just the opposite as the way that lines of constant pressure appear on a TV diagram or a T question mark diagram. So this is our pressure volume diagram that we have drawn, and you'll notice that the saturation dome pretty much looks the same, and the left-hand side is the saturated liquid line, the right-hand side is the saturated vapor line, and we use V sub F to mean saturated vapor, or excuse me, saturated liquid specific volume, and V sub G to represent saturated vapor specific volume. But the one difference between the pressure question mark plot and the temperature question mark plot is the way that the isobars are drawn, or the isomers. So, for example, the line of constant temperature on a P question mark plot is essentially just the opposite as a line of constant pressure on a T question mark plot. And the lines of constant temperature basically look like this, right? You start up high, come down, constant temperature through the phase change region, the two-phase region, and then we go off in the southeast direction of the plot or of the plane. And so if I draw two lines of constant temperature here, T1 and T2, then of course, similar to the temperature question mark plot with lines of constant pressure, T1 is greater than T2. And so this is written correctly, unlike how I had it written above for the temperature question mark plot. So one thing to note is that it's very important to remember the general shape of these curves, because as I'll demonstrate in just a little bit, these curves can be incredibly helpful with trying to determine properties of a substance using the tables. And like I said, I'll demonstrate that to you later on. Okay, so now that we have a general idea of the phase diagrams that we'll be using this semester, we can now introduce a really important concept, which is called the state postulate. Okay, so to set the stage for the state postulate, let's suppose that I have a container of water, and this water that's in the container, and suppose it's a sealed container, let's suppose that the water has a pressure of 50 kPa and a temperature of 300 degrees Celsius. And let's suppose that I asked you that I want to know what its specific volume is. If I say pressure is 50 kPa and temperature is 300 degrees C, can you tell me what the water's specific volume is? What about its specific internal energy, or its specific enthalpy, or its specific entropy? Could you tell me any of these properties based on me telling you that the water is 50 kPa pressure and 300 degrees Celsius temperature? In other words, can we get all that information knowing just the two properties, pressure and temperature? Well, the answer is yes. And the caveat to that is that the answer is yes if the two properties that we know about the substance are independent and intensive. Okay, so what does this mean? What does it mean to say that the properties are independent? You already know what it means for the properties to be intensive. That means that they're mass independent. But what does it mean for the property itself to be independent? Well, what it means is that if I can vary the property without having to vary any other property, then that property is independent. So almost all of our properties that we study are actually, in fact, independent. There's one exception, and that is temperature and pressure during the phase change region. As we know, we cannot change temperature without changing pressure in the phase change region, in the two-phase region. And vice versa, you can't change pressure without changing temperature in the two-phase region. But outside of the two-phase region, temperature and pressure are independent properties, as are entropy, enthalpy, internal energy, and specific volume across all phases. Those four properties are always independent: specific volume, internal energy, enthalpy, and entropy. But what does it mean to say that if we have two properties that are independent and intensive, we can determine all the other thermodynamic properties? Well, the fact that I can do that, right, that is, if I have just two independent properties, I can tell all the other thermodynamic properties of the system. That principle is called the state postulate. And the state postulate basically says that a simple thermodynamic system is fully characterized if only two independent properties are known. So all I need to know are two independent properties of my system. And if I know those two independent properties of the system, I can determine all the other thermodynamic properties. I can determine specific volume and entropy and enthalpy and entropy if I know temperature and pressure, assuming temperature and pressure are in fact independent. Okay, well, if this is true, if the state postulate is true, then what are specific volume, internal energy, enthalpy, and entropy of water at a pressure of 50 kPa and a temperature of 300 degrees C? How do I actually get these values, right? How do I actually get specific volume or internal energy or enthalpy or entropy if I know the pressure and temperature? Where do I get that information from? Well, this is where the thermodynamic tables come in. So we have something which is called the tables of thermodynamic properties, okay? And these tables, which we often will call just thermodynamic tables for short, are collections of discretized property values of various substances sorted by temperature and pressure. And the tables typically include all of the properties that we would need, such as specific volume, internal energy, enthalpy, and entropy. So there is a set of tables for water that include the specific volume, specific internal energy, specific enthalpy, and specific entropy of water at different temperatures and pressures. And we can go to those tables knowing pressure and temperature, and we can look up the temperature and pressure and find the corresponding properties that we need to know. So every substance in the universe could have a thermodynamic table, right? Every substance in the universe has thermodynamic properties. And so we could, for every single substance, tabulate, determine and tabulate all of the property data for those various substances, okay? There could literally be countless numbers of tables. But fortunately for us, this semester, we're only concerned with a few tables, okay? Specifically, the few tables that we're concerned with correspond to the substances that we'll need to study this semester. So the substances that we will be concerned with include, first and foremost, water. This will be the substance that we study the most this semester. Secondly, and to a much lesser extent, we'll need to know R134A. And R134A is basically what we call a refrigerant, and it's used in air conditioning systems, in refrigerators, and deep freezers, and basically anything that operates on a refrigeration cycle. We'll talk more about the refrigeration cycle later on this semester. Therefore, it's necessary for us to be able to determine properties for a refrigerant, which R134A is an example refrigerant. The other substance that we'll study this semester, which they're not technically a specific substance, but because they possess general characteristics, any substance that can be classified as such will have well-described behavior for. And so that third class of substances are what we call ideal gases. So what that means is that ideal gases have very specific and generalized behavior. And so if we can classify a substance as an ideal gas, because that ideal gas has generalized behavior, we can correspondingly determine the properties for that ideal gas. Okay, so the textbook contains all kinds of tables, all kinds of thermodynamic tables, and we're going to use some of them, but we're not going to use all of them. And basically the tables that we'll use, most of the tables that we'll use, this isn't a complete list that I have here, though there will be some additional tables that we'll use throughout the semester. But basically, tables A1 and A2 are used for when we do ideal gas analysis. So that's going to come up later on in the semester. That's not part of today's discussion. Table A3 is used for solids and liquids when we're analyzing solids and liquids. Tables A4 through A8 are what we call the water tables. We're going to come back to these in just a little bit. And tables A11 through A13 are what are called the R134A tables. Okay. Now, if I look up here at this list of three substances, water, R134A, and ideal gases, these two substances, water and R134A, are usually involved in processes where they change phase during the process, or they change phase during a cycle, a collection of processes. Therefore, both water and R134A, we have to be concerned with the two-phase mixture behavior and the two-phase mixture properties. Ideal gases, on the other hand, are basically always ideal gases, right? In other words, they never change phase during the process. They can always be treated as being a gas, and in addition to that, being an ideal gas, okay? But so what this means for water and R134A is that our tables correspond to the substance's two-phase region, the saturation region. And so what I've done is I've taken this list of tables for both water and R134A. So the water tables includes table A4, table A5, table A6, table A7, and table A8, so 5 tables. And R134A, tables A11 through A13, has 3 tables, A11, A12, and A13. So where all of those various tables correspond to the substance's phase, I've provided in these two plots here, where this is meant to represent the saturation dome for water. And if I need to know property data for water when it's a compressed liquid, then I go to table A7. If I need to know property data for water when it's a saturated mixture, then I go to either table A4 or A5. We'll talk about the differences between these two in just a moment. If my substance's phase is a superheated vapor, then I go to table A6. And if my substance is a saturated solid vapor two-phase mixture, in other words, if it's sublimating, then I go to table A8, okay? We very rarely, if ever, will use table A8. We will mostly use tables A4, A5, and A6, and to a lesser extent, table A7. If the substance is R134A, then notice we don't have a table for compressed liquid R134A, nor do we have a table for the saturated solid vapor R134A. But we do have tables for when R134A is liquid vapor saturated, so the two-phase liquid vapor mixture region. That is tables A11 and A12. And again, I'll correspond to why there's two tables for the saturation region in just a moment. And then if the R134A is a superheated vapor, then we go to table A13 to get the property data for that substance in the superheated vapor region. Okay, so when you look in the back of your book, you'll notice that you actually have two sets of tables. One set of tables contains the International Standards Units data, and the second table includes the property data with English units. And the English unit tables are annotated with the letter E, but you do want to pay close attention to that, because if you have metric units and you're looking in the English tables, obviously the values that you look up will be incorrect. So you want to pay close attention to that. Okay, so as we've already pointed out, we noted that there are actually two tables for the saturation region, right? We had tables A4 and A5 for water, and we had tables A11 and A12 for R134A. So there's really just a very small difference between these two tables, okay, between A4 and A5 and between A11 and A12. They basically contain the same data, that is, they contain the saturation data for that substance, but the way that they're sorted is different. Table A4 is sorted by the saturation temperature of the substance, whereas table A5 is sorted by the saturation pressure of the substance. And likewise, table A11 is sorted by saturation temperature for R134A, and table A12 is sorted by saturation pressure for R134A. Okay, and that's what I have summarized down here. The data is the same, but because the data is sorted differently, the values that are in the table will be different. Okay, but it's all still capturing the same two-phase mixture data for that specific substance. Okay, so now that we know something about the tables and we have a general idea of what different tables provide what information, now comes the big question, and often the question that can cause a lot of consternation for students in thermodynamics, which we certainly wish to avoid at any semester, and that is, how do we use the tables? Okay, so here's the question, right? How to use the tables? Well, let's first of all consider our earlier example. Well, in fact, actually, before I get into this example, let me actually show you the tables and just kind of walk you through them so that you have a general idea of what they look like. Okay, so if we take a look here in the back of your book, you will have table A4. Okay, and if you bought the 7th edition, either the full version or the condensed number of chapters version, that's the custom version for Texas A&M, then table A4 should start on page 916. If it doesn't, don't worry about it. You might have a different version of the textbook, but no matter what, you should at least have a table A4 in the back of your book, okay? And you'll notice that the title of this table is Saturated Water Temperature Table. So what that means is this is giving the data for water when it's saturated, that is the two-phase region, and the data is sorted by saturation temperature. Okay, so let's look at what information is included in this table. Now, first looking at it, it can be very overwhelming. I mean, we're just looking at a ton of information here, and so it can seem somewhat intimidating. There's no need to let it intimidate you. You'll be able to work through this just fine. We just need to be patient with it, okay? So the first thing that you'll notice is that the column on the left-hand side is temperature, okay? So, and because this is a saturation table, this would be called the saturation temperature, okay? Right next to that column of data is the saturation pressure. Remember that the temperature and pressure when the substance is saturated are dependent, okay? So as I change temperature of the substance, the pressure of the substance necessarily must also change, or vice versa. If I were to change the pressure of the substance, then the temperature of the substance also changes, okay? But you can get some connection with this data by looking at the saturation pressure for a temperature of 100 degrees C. And we know that water boils at 100 degrees C in atmospheric conditions, when pressure is atmospheric pressure. And look at what value is right to the right of when water boils at 100 degrees C. A saturation pressure of 101.42 kPa, so about 100 kPa. Atmospheric pressure is defined as 101.42 kPa, and so this is the temperature at which water boils at atmospheric pressure, which is 100 degrees C, which is what we know from our own personal experience. So that's our temperature data, our saturated pressure data, and now the next sets of data all correspond to the four major properties that we'll study this semester. So there's the specific volume data, there's internal energy data, there's enthalpy data, and then there's entropy data. And you'll notice that there's two columns, at least two columns for each property. There's the saturated liquid column, and there's the saturated vapor column. So the data in the saturated liquid column is telling us the values of the substance when it's a saturated liquid as a function of the saturation temperature, okay? The saturated vapor column is telling us the values of the specific volume when the substance is a saturated vapor as a function of temperature. So we have the saturated liquid specific volume, the saturated vapor specific volume, the saturated liquid internal energy, the saturated vapor internal energy, saturated liquid enthalpy, saturated vapor enthalpy, saturated liquid entropy, and saturated vapor entropy. Now for internal energy, you'll notice that there's this third term for internal energy, enthalpy, and entropy called the vaporization energy. So this U sub Fg is just the difference between the saturated vapor and saturated liquid internal energy, or HFG, the enthalpy of vaporization, is the difference between the saturated vapor and saturated liquid enthalpies, and the same is also true for the entropy of vaporization. You all have heard of the vaporization enthalpy, the enthalpy of vaporization. This, for example, is the amount of energy that must be either added or removed from a substance to cause complete phase change. So, for example, at 100 degrees C, the enthalpy of vaporization is 2,256.4 kilojoules per kilogram. What that means is this is the amount of energy that has to be added per unit mass in order to completely vaporize liquid water at 100 degrees C, or this is the amount of energy that must be removed from vaporized water to condense it completely to liquid water at 100 degrees C, whichever way you want to look at it. If you turn a couple of pages, you'll then go to page 918, which is table A5, which is the saturated water table. So again, this is data in the two-phase region for water, but now it's sorted by pressure. Table A4 is sorted by temperature, so there's temperature in the left-hand column. Table A5 is sorted by pressure, so the pressure is in the left-hand column. And again, just to make a connection, we can find where atmospheric pressure is, right? So atmospheric pressure is just a little bit above 101.325 kPa, and the boiling temperature at that pressure is about 100 degrees Celsius, 99.97 degrees Celsius. But you'll notice that all of the other data is the same: saturated liquid specific volume, saturated vapor specific volume, internal energy, enthalpy, and entropy. All the data is the same, but the values are different, right? The values are different because the data is sorted by saturation pressure as opposed to being sorted by saturation temperature. Okay, so again, if we just move on a little bit further, turn a couple more pages, we come to table A6. And table A6 is now providing the property data for when water is a superheated vapor, right? So table A6 is titled the superheated water table. Now, when we get to table A6, when we get to the superheated vapor region, temperature and pressure of water, temperature and pressure of any substance become independent again. They're no longer dependent on each other. So it's entirely possible to change the pressure of a substance without necessarily changing the temperature. So table A6 and table A13, if this were for R134A, are organized by what we call pressure subtables. So this is a pressure subtable where all of this data corresponds to a pressure of 10 kPa, 0.01 megapascals. And all of the data in this pressure subtable correspond to a pressure of 50 kPa, 0.05 megapascals, okay? So on and so forth, 100 kPa, 200 kPa, 300 kPa, 400 kPa, and it's the same story as you flip through the next few pages of table A6. And so, of course, you can see that at this line of 200 degrees Celsius, we could certainly have water at 200 degrees Celsius and 10 kPa, and we can also have water at 200 degrees Celsius and 50 kPa, and we can have water at 200 degrees Celsius and 100 kPa. And if we just keep on doing that, what eventually we'll find out is that there's going to come a point where we cannot have water at 200 degrees Celsius. If we get to such a high pressure where even at that very high pressure water doesn't vaporize yet, it will no longer appear as a temperature on the left-hand side of table A6. Okay. Now there's a few other interesting features to point out in this table. The first is that you'll notice that the top of every single temperature column is listed SAT. Okay. So the data that's listed for the SAT line, what that SAT stands for is saturated vapor. So these are the data for saturated vapor water, okay, at the various pressure subtables. And you'll also notice that in parentheses next to the pressure listing, there's a temperature that's listed. That's the saturation temperature of water at that pressure, okay? So let's test this. What this means is that I should be able to go to table A5, because that's my saturation table, and I should be able to see that the saturation temperature is 45.31 degrees Celsius, and I should be able to show that the saturated vapor specific volume is 14.67, okay, at 10 kPa. Well, let's go to table A5 and see if that's true. So remember, table A5, 10 kPa, 45.31 degrees Celsius, 14.67 saturated vapor specific volume. Let's go to table A5, and here's 10 degrees Celsius. And lo and behold, the listed temperature is 45.81 degrees Celsius. I couldn't read the writing or the typing on the other page, but that's our saturated temperature, so that corresponds correctly. And our saturated vapor specific volume is also the same, 14.67. And if we were just to carry this experiment a little bit further, we could look at, say, the saturated vapor entropy, 8.1488. So when we go to table A6, we see that it's the same, 8.1488 kilojoules per kilogram Kelvin. So that top line of each of the subtables corresponds to the saturated vapor properties at that pressure. Okay. Now you'll also notice that some of the subtables have blanks, right? So there's this subtable here doesn't have any data for 50 degrees Celsius. Why? Because water at a pressure of 50 kPa and a temperature of 50 degrees Celsius is a liquid. And we know that because the saturation temperature for water at 50 kPa is 81.32 degrees Celsius, but 50 degrees C is lower than 81 degrees, and so of course that would mean that it's a liquid. And so it's not a superheated vapor, so the data is not included in this table correspondingly. Okay, so then finally the last table that I'll briefly talk about is table A7. This is the compressed liquid water table. This is if we're to the left of the saturated liquid line. So one thing to note here is that the pressures are very high, 5 megapascals, 10 megapascals, 15 megapascals. We'll talk about that a little bit later on. And then the last water table is table A8, which I didn't even include in the discussion just because we very rarely ever use table A8, if ever, during this semester. Okay, so how exactly, now that we have an idea of what the tables look like, how is it that we actually use the tables? Okay, well, let's consider our earlier example where we want to know the specific volume, internal energy, enthalpy, and entropy of water at a pressure of 50 kPa and a temperature of 300 degrees C. How do we get started? How do we even use these tables? Well, I like to follow this recipe where we have a four-step recipe. And so step number one is that we first of all want to determine the substance, right? If I go back to this list up here, you know, we say that we study water, R134A, ideal gases, right? If the substance is water, we want to use the water tables. Don't try to apply ideal gas law behavior to water. Or if we have R134A, we want to use the R134A tables. We do not want to use the water tables. We do not want to treat R134A as an ideal gas. So the first thing to do is to recognize the substance and make sure that we use the tables appropriately. Okay? So that's step number one, determine the substance. Step number two is to determine the phase. Determining the phase, if you can determine the phase for your substance, you will find using the tables a lot less frustrating, okay? A lot of times folks really get hung up on knowing which table to look in, and they just sort of kind of guess, and if you're not guessing correctly, then you get discouraged, and that can be a very frustrating feeling. You can solve all of that by determining the phase of the substance, and I'll show you how you do that as part of this example. Once you know the phase, then knowing the table to use is really straightforward. So that's step number three. And then once you determine the table, then you can just determine the property. Okay, you can just look up the property in the table. Okay, so let's use our example, right, of 50 kPa, 300 degrees Celsius, right? So first of all, step number one, determine the substance. Well, I told you it's water, so that's easy. The substance is water, okay? But again, let me just remind you that if you're told that the substance is water, use the water tables. Do not apply ideal gas behavior. We haven't learned about ideal gas behavior yet. We'll do that next week. But folks love to apply ideal gas law to every substance. That's not going to work. Okay, if you have water, you need to make sure that you use the water tables. If the substance is R134A, you need to make sure that you use the R134A tables. Okay, step number two, determine the phase. Now this part's harder, okay? This is kind of the harder part of determining the properties of a substance, but once you learn how to determine the phase, this really becomes straightforward and easy, okay? And determining the phase is particularly straightforward if you remember your T question mark and P question mark diagrams. So, how can we use these diagrams to determine the phase of the substance? Well, let's look at our TV diagram, right? We have our saturation dome, and I'm going to draw a line of constant pressure. And what I'm going to do is I'm going to say that this line of constant pressure corresponds to a pressure of 50 kPa, okay? Now, at a pressure of 50 kPa, I can go to table A5 and I can look up that the saturation temperature of water at a pressure of 50 kPa is 81.32 degrees Celsius, okay? How do I do that? Well, let's go to table A5 and let's find 50 kPa. So here we are, table A5, there's 50 kPa, and there's the saturation temperature for water when it's at 50 kPa, 81.32 degrees Celsius. And that's what I have written right here, okay? The saturation temperature of water at a pressure of 50 kPa is 81.32 degrees Celsius. So that temperature is corresponding to when the pressure is 50 kPa. When water is at a pressure of 50 kPa, it saturates or it boils at 81.32 degrees Celsius. So that allows me to position the temperature and the saturation temperature and pressure of water when the saturation pressure is 50 kPa, okay? But my substance is at 50 kPa, but I don't know if it's saturated or not. What I do know is that it's at 300 degrees Celsius. Well, 300 degrees Celsius is greater than 81.32 degrees Celsius, so I can draw that up higher on the y-axis. And so because my substance is somewhere along this line of 300 degrees Celsius and somewhere along this line of 50 kPa, right, my substance is going to be where those two lines intersect each other, which is right here, okay? So our substance, based on this analysis on the TV diagram, is in the superheated vapor region. I could also do this on a PV diagram. If you'd like to see it done on the PV diagram, it's the same idea. So again, what I do is I draw a line of constant. I start with drawing my line of constant temperature, in this case of 300 degrees Celsius. And then I need to find out what the pressure of water is when it's saturated at 300 degrees Celsius so that I can position where this line of 300 degrees Celsius cuts through the saturation dome. So I find out the saturation pressure of water at a temperature of 300 degrees C by going to table A4. So I go to table A4, I find 300 degrees C, and I look in the saturation pressure column and I see that the saturation pressure of water at 300 degrees C is 8,587.9 kPa. So that means that when water is saturated at 300 degrees C, this part here, its pressure is 8,587.9 kPa. Well, 50 kPa is obviously much less than 8,587.9 kPa, and it doesn't really matter where I draw it. I just arbitrarily draw it here, and I bring my line of 50 kPa over, and where that line intersects the line of 300 degrees C, that indicates what phase the substance is in. And so, of course, we've confirmed again that our substance is in the superheated vapor region. So we've determined that the phase is superheated vapor, and once you know the phase of your substance, knowing which table to look in becomes straightforward, because we know table A6 corresponds to the superheated vapor region, right? So we can go to table A6, and we can find, we can look in our 50 kPa subtable and find a temperature of 300 degrees C. And so when we do that, if we go up to table A6, So here's table A6, and here's the 50 kPa subtable, and here's 300 degrees C. So our specific volume is 5.2841 cubic meters per kilogram. Our internal energy is 2811.6 kilojoules per kilogram. Our enthalpy is 3075.8 kilojoules per kilogram. And our entropy is 8.5387 kilojoules per kilogram Kelvin. And so those are the various values that I have written down here at the bottom. These are just pulled out of table A6 based on pressure of 50 kPa and a temperature of 300 degrees Celsius. Okay, so that's all well and good, right? But what happens if we were to determine that our property or our substance is not a superheated vapor or is not a compressed liquid, but is in fact a two-phase mixture, right? What if, for example, our substance is somewhere under the dome, okay? Well, in that case, we have to introduce a new property, which is only defined when the substance is saturated, and this new property is called quality, okay? So if you recall the state postulate, which says that we have to have two independent properties to fully characterize the system, to fully thermodynamically characterize the system, right? And we recall that we actually lose an independent property when the substance is saturated because temperature and pressure become dependent on each other, right? They lose their independence in the two-phase region, okay? So because of that, because of the loss of an independent property and the need for two independent properties to fix the state based on the state postulate, we develop a new independent property that exists only when the substance is saturated. And this new independent property is called quality, okay? Now this quality is not to be confused with the quality that we use to characterize the useful work, the useful fraction of energy, okay? This quality is meant to only characterize the amount of vapor, saturated vapor, that exists in a two-phase mixture of a substance, okay? So quality, and we use the letter X to indicate quality, is an independent property of a saturated two-phase mixture that quantifies the fraction of the mixture that is saturated vapor. The balance of the mixture would be saturated liquid, okay? So I've created a little diagram with a chart here to kind of summarize the various values that quality could be. And first of all, if we're to the left of the saturation dome, we're in the compressed liquid region, so this is all a liquid here. Well, the substance isn't saturated, so quality is undefined. Quality is only defined when the substance is saturated. Likewise, we could have a situation where now the substance is saturated, but it's only saturated liquid, right? In other words, it's right on the left side line of the saturation dome. It's right on the saturated liquid line. In that case, the substance is all saturated liquid. There's no saturated vapor, and the quality would be 0. Okay, remember that quality is quantifying the amount of saturated vapor in the mixture. There's no saturated vapor, so the quality is equal to 0. If we have a mixture of saturated vapor and saturated liquid in the system, then quality will be somewhere between 0 and 1. And if we are saturated and the substance is all saturated vapor, there's no saturated liquid, this corresponds to when quality is exactly equal to 1. And if the substance is a superheated vapor, it's not saturated, then quality is undefined. Again, remember, quality is only defined when the substance is saturated. So compressed liquid, quality is undefined. The substance is saturated liquid, quality is equal to 0. If it's a two-phase mixture, quality is somewhere between 0 and 1. If it's a saturated vapor, quality is exactly equal to 1. And if it's a superheated vapor, then quality is undefined. So we can mathematically define quality as follows. It's the mass of vapor divided by the total mass in the system. So the total mass is, of course, the mass of liquid plus the mass of vapor. And using this definition, we can basically determine our other four properties, specific volume, internal energy, enthalpy, and entropy, using one of these four equations, which are often called the quality equations. Okay, so what it says is that the specific volume of the two-phase mixture is equal to the saturated liquid specific volume plus the quality times the difference between the saturated vapor and saturated liquid specific volumes. The equations for internal energy and enthalpy and entropy look very much the same. The difference is that quality is being multiplied by the internal energy, enthalpy, or entropy of vaporization, right? So UFG, remember, is the difference between the saturated vapor and saturated liquid internal energy. HFG is Hg minus Hf, and SFG is Sg minus Sf. And just a real quick tangent to throw in here. If you remember the definition of the critical point, we said that it's the point above which a substance does not undergo equilibrium phase change. What that means is that the substance cannot exist as a two-phase mixture, right? In other words, it's not possible for that substance to have quality. It's either a liquid or it's a vapor. And the phase change between the two, between liquid or vapor, happens spontaneously. You can't have this region of two-phase mixture. And what's also kind of interesting is that phase change above the critical point is rather unpredictable, right? So there are different perturbations that can lead to different ways that phase change occurs. It doesn't happen under what we call equilibrium conditions. Okay, now the other issue that we'll run into sometimes is that we'll know property data for a substance that the data do not nicely align with the tabulated data in the tables, okay? In other words, and I've got an example to show you exactly what I mean here. So what we have to do in these cases is we will do what is called linear interpolation. Okay, we'll linearly interpolate to get the other property information. So for example, suppose that we have water at a pressure of 500 kPa and an entropy of 7.2 kilojoules per kilogram Kelvin. And the question is, what is water's enthalpy at this state, right? With 500 kPa pressure, entropy of 7.2 kilojoules per kilogram Kelvin, what is water's enthalpy? Okay. Well, if I go to, so I don't show it here, but water is a superheated vapor at this condition, okay, and we can go over this in class as to how I determine that this is a superheated vapor. But if I go to table A6, since it's a superheated vapor, and I find the 500 kPa pressure subtable, so here's 500 kPa, and I look down the list of entropy, and I'm looking for 7.2, but I don't see 7.2 exactly. I see 7.06, and then I see 7.27. I don't see precisely 7.2. 7.2 falls somewhere between 7.06 and 7.27, okay? And when I look at the enthalpy values, the enthalpy values change quite drastically, and so I have to come up with some means of being able to estimating the enthalpy when the entropy is equal to 7.2 kilojoules per kilogram Kelvin. So how do I do that? Well, that's when I use linear interpolation. So what is linear interpolation? Well, the basic idea is that we assume that the behavior of a property as a function of the other property is linear. So in other words, the change in enthalpy as we go from an entropy of 7.0610 to 7.2725 will change linearly from 2855.8 to 2961.0. And so I represent that idea on this sketch here, right? So this isn't a phase diagram. This is just to show the example of linear interpolation. So we have enthalpy on the y-axis. We have entropy on the x-axis. And I can put 2 points on here, right? 2 points that I absolutely know based on my table data, okay? I know that when the entropy of water is 7.0610, its enthalpy is 2855.8. So that'll be point A on my diagram, 7.0610, 2855.8. Okay. Likewise, I know that when the entropy is 7.2725, the enthalpy is 2961.0. So that'll serve as point B, 7.2725, 2961.0. And with linear interpolation, what I do is I assume that the change in enthalpy with entropy between point A and point B is linear, perfect straight line. Well, the entropy of the substance or the state that we're interested in, the entropy is 7.2, which is, of course, somewhere between 7.06 and 7.27. So I just sort of sketch 7.2 as being located here. And the enthalpy, therefore, of our state is somewhere between 2961 and 2855. And it's this enthalpy that we're trying to solve for. Okay. So since we drew a straight line between point A and B, and because point C is also on this straight line, what that means is that the slope of line AB is the same as the slope of line AC. So we can set those two slopes equal to each other. So slope, of course, is the change in y divided by the change in x. And the slope of AB is equal to the slope of AC. So the change in y of AB is 2961 minus 2855.8. And the change in x of AB is 7.2725 minus 7.0610. So that's what I have written here. And then the change in y of AC is h, that's what we're trying to solve for, minus 2855.8. And the change in x of AC is 7.2 minus 7.0610. So when we plug all of this into a calculator, we get that the enthalpy is equal to 2924.9 kilojoules per kilogram. And so that would be the enthalpy of our state based on linear interpolation. You're going to use linear interpolation a lot this semester, okay? And if you have a calculator that has linear interpolation program on it, you're more than welcome to use it. And if your calculator doesn't have that, then you're more than welcome to program your own linear interpolation. It's not too bad to do. You just use this basic equation that I have here. Just program that in, using various variables of inputs and such, and you can program that in very nicely to be able to do linear interpolation for you. Okay, the last thing that we need to talk about is the idea of what we call the saturated liquid approximation. Okay, and this won't come up that often, but it comes up enough where you need to be aware of it. And what happens is sometimes you'll have a substance that is a liquid, but it's either not at a high enough pressure to be in a compressed liquid table, for example, table A7 for water, or you may not have a compressed liquid table, right? So for example, with R134A, we don't even have a compressed liquid table. In this case, we invoke what is called the saturated liquid approximation, which assumes the saturated liquid properties at the substance temperature. Okay, so what does that mean? Well, let me explain. Suppose that we have water at 200 kPa and a temperature of 20 degrees C. Okay, well, again, I can show you this in class, but I know that water at that temperature and pressure is a liquid. And if we go to table A7, what we find is that the lowest pressure in table A7, the lowest pressure subtable, is 5,000 kPa. Really high pressure, much higher than the 200 kPa that our substance is at. Okay, so the lowest pressure in table A7 is 5,000 kPa. Our pressure is only 200 kPa. And if we assume these values, then our data could be very wrong, right? In other words, we could introduce error in our analysis by assuming these values for water at that pressure and temperature. So we'd like to get a little bit better approximation on our property values. So that's when we invoke the saturated liquid approximation, which basically says that we assume that the specific volume of water at a temperature of 20 degrees C and a pressure of 200 kPa is approximately equal to the saturated liquid specific volume at a temperature of 20 degrees C, which would be 0.001002 cubic meter per kilogram. And we can do this for all of our properties. We can do this for internal energy, enthalpy, and entropy, where we assume that the internal energy of water at 20 degrees C and a pressure of 200 kPa is approximately equal to the saturated liquid internal energy at 20 degrees C, and the same for enthalpy, and the same for entropy. Okay, so with that, that concludes our lecture number 8. So again, please remember to bring your textbook on Thursday. We're going to go through various examples that'll help you basically use all of the information that we just went over. And also please bring your homework number 4 sheet so that you'll be able to make good use of the exercises that we plan to do in class. Thanks very much for your attention, and I look forward to seeing you on Thursday. If you have any questions, just send me an email. Bye-bye.